Thanks for the introduction. Hi, my name is Luis Vargas. I'm excited to show you this collaboration effort between the University of Florida and the University of Richmond. Now, the title of this talk is Mitigating Risk While Complying with Data Retention Laws. This seems like a very weird title for a security talk, so let's see exactly what we mean by this. Let's say we have an enterprise, and inside this enterprise, we're storing a whole bunch of data. Amongst all the data, we have some sensitive data that no longer has a business purpose, or it used to have, but we no longer access it anymore. Your question right now should be, why are we storing this data anymore? Seems unnecessary, right? Well, that's because sometime in the future, a legal authority is going to want to have access to that data because of data retention laws. And these data retention laws make it so that a company or an enterprise must keep outdated data for a very long time, say 25 months, 5 years, 6 years, or even longer, so that they can use that data to perform some type of auditing of the company in the future. Now, there's many different examples. For example, in the US, we have HIPAA, Sarbanes-Oxley, and many others. And I know Canada and other countries have something in place just like that. So because we're talking about security, we know that nothing's going to be perfect. And that before the legal authority can actually get access to the data, we're going to have a data breach. And this happens for many different reasons, whether that be some misconfiguration or some insider, or actually something as silly as, let's say, a storage tape falling off a truck on its way to its delivery. So once the data breach happens, it's only a matter of time before the attacker can actually get access to the data. And if we're not using any protection, then the time between the data breach and the access to the data is actually zero, just because the data is already exposed. And it's important for us to basically differentiate between these two times, because the enterprise that we're talking about is a good enterprise, and they want to provide some proactive mitigation techniques to the data exposure so that the clients or themselves are not exposed as much. So tying it back to the title, we're just mitigating the damages of the exposure of this data when we're talking about sensitive information being stored by the data retention laws. So how can we do it? Well, let's go over some of the most, obvious solutions right now. Yeah, we have sensitive data. It stands to reason that we should probably encrypt it somehow. Symmetric encryption, let's just say. Well, if we encrypt it using symmetric encryption, then when the data breach happens, this time difference between both of the events is quite long, or until the key gets exposed. And that's actually bringing us to our very first problem, key management. In some systems, when we encrypt some data, the key actually gets stored in the same place as the encrypted data. So when the attack happens, well, the key gets exposed along with the data. And another problem that happens with symmetric encryption is that, well, we have to encrypt this data by sharing a secret with the legal authority. Now, while the data retention laws tell us that we have to that we have to show this data to the legal authorities, it does not tell us to which legal authority we're going to keep. We have to show it to. So there's different legal jurisdictions, for example, local, state, or federal, that might want to get access to this data. So we don't really know under which key we should probably encrypt it. And the same is true for public encryption, because although every single legal authority might have a public key, we just don't know under which key we should encrypt our data. So traditional encryption is not going to help us out. How about something that's a little bit less traditional? So secret sharing or key escrow. In secret sharing, we're encrypting our data, and we're splitting our keys into different chunks and storing those chunks into different devices inside or outside of the network. Now, if we're storing all the chunks inside our network, when the data breach happens, we're assuming that the whole enterprise is basically under the control of the attacker. So that won't really help us out. And if we store these keys outside of the network, well, then we're introducing actually a new problem, and that is we're storing this key. We're storing these keys with a third party, and while that might be okay in some cases, in our case, it's really not. Just because we have to store this data for a very, very long time, anything can happen to a third party, whether that be they become unstable, whether they go rogue, or whether they go bankrupt. In any of those cases, well, we're still on the hook for the data, but we just can't retrieve it anymore. All right, so let's set encryption aside for a second, and let's talk about, well, we're not accessing this data, so let's just store it offline and call it a day. Well, I really wasn't kidding when I said that a data breach happened because a storage tape fell off a truck on its way to being archived. My point is this. All of the methods that I just talked about are not going to give us this concrete time for the enterprise to actually react to the data breach. So just to summarize what the problems is that we're talking about, we have an enterprise that's storing a whole bunch of data that's not being accessed anymore because of the data retention laws. And before the legal authorities can actually get access to that data, we're going to have a data breach. We're not talking about how the data breach happens. We're talking about what we can do afterwards. Now, we're also assuming that any locally stored secrets, and by local I mean in the system or in the enterprise, are going to be leaked. So we can't store any secrets. And because we don't know to which legal authority we need to give this data afterwards, we can't really share a secret with them. Or if we do, we have to share it with everybody, and that makes key management a whole big nightmare. And because we're talking about an enterprise that wants to be good, they want to have this mitigation window as part of their security margin. And finally, when we give this to the legal authorities, we want to show some type of proof of compliance that basically says, hey, we have the data, but we're just taking the precautionary protections to protect ourselves. So to meet those challenges, we propose using the Dragchute escrow system, where the name in and of itself implies that we're dramatically slowing down any fast-moving object. So our goal here is to mitigate rather than to eliminate the risk of data exposure. And we do so by not storing any secrets. So we're completely bypassing this whole key management issue. Also, we're providing this predictable time delay that actually allows us to concretely differentiate between when the data breach has happened and when the data breach can actually be considered compromised. Now, we do so by requiring non-parallelizable work. So it doesn't really matter how many resources you have available. You're just as powerful as a single processor. And when we're storing the data, we require no interaction with the legal authority because, again, we just don't know who the legal authority is going to be in the future. So we're talking about what happens after a data breach. There's two cases we need to worry about. A passive case, where basically our adversary just wants to get immediate access to the data, or an active case, where the adversary can either modify data that's already in there, or they could create its own data. So for the next couple of slides, we're going to focus more on the passive case, and we'll eventually build up to the active case. So the Dragchute escrow system can be thought as 4 different high-level functions. First, we have generate. Here we're creating all our secret and public parameters. So basically our secret keys, our public-private key pairs, strong primes, so on and so on. This parameters then get passed to the lock function, where along with this user-defined time value, we actually lock our data for that specific time. And as soon as we're done with the lock function, any type of secrets that might allow immediate access to the data will get deleted. Now, the unlock function basically works for that specified time that was specified during the lock part and gets back the data. And attest gives us this proof of compliance as we've been talking about. Now, we're going to focus on the lock and unlock part mainly, just because generate simply gives us all of our randomness, and attest gives us basically checks that everything in the lock function was computed correctly. So how do we encrypt it? How do we lock this data? At a high level, we basically have a secret key, we have a plain text, and we encrypt the data using that secret key. Simple. Using some type of traditional encryption, symmetric encryption. However, we're not done there yet. We still want to create this time window, this programmable time window. So once we're done with that process, we need to do some type of key encapsulation method to create the time window or this time lock container. So to create this time window, or creating this time window is by no means a new problem. There's been a lot of research in this field already. For our Dragchute escrow system, we actually built on top of work by Boners and our time commitment paper and the Blum-Blum-Shub pseudo-random sequence generator. Essentially, what we want to do is grab the pseudo-random key stream, and somewhere in there, we want to XOR our secrets against it. And whatever's left behind is actually our time lock container. So the pseudo-random key stream has to have a certain amount of properties behind it. And the first two is that it has to be deterministic and sequential. So how do we compute this? Well, essentially what we get is the output of the previous step, we get the square of that value, and then from that square, we get the modulo of that square. After that, we get the least significant bit and store that value as the actual value for the position in that key stream. So this is deterministic because we're able to basically define the modulo on all those numbers. And it's also sequential because we need to have some type of knowledge of the previous value beforehand. And this method of doing this sequential squaring, or squares of squares of squares, is a process that's inherently unparallelizable. So this is why we can say that even though you might have a lot of resources with you, you're just as powerful as your single processor. So after t steps later, and t is this user-defined time value that gives us our time window, we finally get to the starting point of where we're going to encrypt our data, or where we're going to XOR our data against. After we get to that point, we just need to do a little bit more work to get enough randomness and finally XOR that randomness against our secret. Now, if we were to do every single one of the sequential computations during the lock function, that will make this process extremely inefficient. However, this is where the third property comes about, and this is the trapdoor property. Essentially, this trapdoor values, or in this case, is the strong prime numbers used to generate the Blum-Blum-Shub pseudorandom key stream, allows us to jump around anywhere in the sequence we want with one single computation. So essentially, we use the trapdoor values to do that one computation, and then again, we just need to do a little bit more work to get enough randomness and XOR that randomness against our key. Once we're done with that process, we delete our key and the trapdoor values. It is at this moment that nobody, and not even us, can actually get immediate access to the data anymore. And that's actually okay, because we certainly don't want the adversary to get immediate access to the data. And we don't really care though if we get immediate access to the data. Remember, we're talking about this data that we're just keeping around but no longer use. So now that we've gone to how the locking works, unlocking is fairly simple to understand. We just have to do the same steps. We have to regenerate this pseudorandom key stream, and somewhere in that key stream, we just remove that, we XOR and remove the blind that we had in the locking process. However, unlike during the lock process where we had the trapdoor values, in the unlock, we actually don't have those values anymore. So we do need to do every single sequential step. And here I want to pause for a second and say that this is a fundamental difference as to how time commitment schemes work. Because in a time commitment scheme, we could actually unlock the data in two different ways, whether that be through the forced open, which basically does all the sequential computations, or through fast open, where we use some store value that allows us to get access to the data quickly again. Here, we're not given an option. Here, we actually do want to just take that long time and compute all those sequential computations. All right. So we just went over how we can stop this immediate access to the passive adversary. But what about the active adversary? And what about this proof of compliances? Essentially, for the proof of compliances, we want to provide some type of data structure that, when verified, commits us to whatever we just presented, basically to the legal authorities. And not only that, but we need to make sure that this type of data structure can be verified in a rapid manner, because once the locking process is done, unlocking takes too long of a time to wait for the data. So we need to show that there's some data in there. And also, because we don't know which legal authority we're going to, because we don't know, because we're not going to interact with the legal authority at when we're storing the data, since we don't know which one we have to interact with, we have to make sure that this data structure or this witness that we create has to be done in a non-interactive fashion. So we're just gonna go over right now the base scheme, or at least what the base scheme is supposed to be. And for the first proof of compliance, we basically want to rapidly assure to the verifier or the legal authority that wants to check the data that if they compute these sequential steps in the unlock process, they'll eventually get back the original committed value inside the time lock container. And to do that, we need to create a witness to the committed value that can prove in a zero knowledge fashion that they know the value that's inside without actually revealing that value. And to make that witness, we actually based it off the same way that Bonet and Neor made their own zero knowledge proof. However, we needed to make a few changes. First, since we're talking about this non-interaction during storage time, since we don't know the legal authority, we needed to make it non-interactive. And that's simply done by doing a Fiat-Shamir transformation. And the second modification we needed to make is, well, we needed to remove any type of dependencies that the witness had on any of the secret values that were stored. Because remember, here we're not storing any secrets. Everybody has to do the sequential steps. So once we do these two modifications and create our witness, then anybody that actually verifies it should be convinced that the witness knows what's inside the time lock container. So for this other two, we're not really going to spend too much time. They're extensions to our proof of compliances, and I strongly suggest everybody to read the paper to see how they work. But for the first proof, we want to be able to prove some type of identity behind who locked the time lock container. And this is important when we're talking about an active adversary that can either modify whatever's inside our systems or create their own data. Because when we're giving this data to legal authorities, we're essentially saying that this is our data. So we need to prove that it is our data. To do that, we're basically committing ourselves to, or proving our identity through a certificate that we commit ourselves in the lock function. Now, for the second proof for the second extension, we want to prove that the decryption process is going to be successful, and to do that, the most simple way of doing it would be to, and to do that, we basically need to create a zk snark that is able to answer the following question, and that is the pre-image of the store hash the key that will decrypt the ciphertext? If we're able to create this zk snark in a trustless manner, and that part is important, then we should be able to also be in compliance with this proof. And the trustless part is important because we don't know which legal authority we have to interact in the future. So we just went over how the system works. Now let's take a step back and talk about how, the performance of the system, or more importantly, were we able to create this time window we've been talking about for our enterprise? So to do that, we basically had to run all of our high-level functions with different user-defined time values. And because we're testing the hardness of time, it took us about 686 computational days to finish all of our experiments. So were we able to create this time lock container, or this time window? Well, as we can see from the unlock graph, as the user-defined time value increases, the time to unlock increases as well, but at an exponential rate. So this tells us that not only were we able to create the time window, but it's also very programmable. We actually know how long it will take when we're locking the data. So this is a system, and we need to worry about efficiency as well. So we also needed to do the same things for the locking. Essentially, what we want is some type of asymmetry between a fast lock and a slow unlock. And we can see that for the very last value, which was about 1 month of computational times of unlocking, it took us only 2 seconds to do that, which is great, which is what we wanted. But we need to do a little bit more, and that is we need to check how this locking mechanism does against traditional methods, say authenticated encryption, so AAD schemes. So to do that, we actually checked with different file sizes how they both would compare. And as the file size increases, the time difference between both the locking mechanism and traditional authenticated encryption is actually almost zero. And that's because so it's almost negligible. And that's because as part of the locking mechanism, we actually do have to encrypt the file. So as the file increases, that becomes the main driving factor of the locking time. So just like any other system, Dragchute has its own limitations. And the first one is, although we have all this proof of compliances, we still can't prove what's behind the data. Essentially, what I'm trying to say is an enterprise is still able to provide fake tax reports or fake data. Proving that is beyond Dragchute Escrow. On top of that, Dragchute Escrow is about buying you time, so mitigating rather than eliminating the risk. As such, Dragchute Escrow should not be thought of as an intrusion detection system. It should just be another tool in the arsenal that a security team may use. And also, because we're mitigating and not eliminating, any private information that was lost during the data breach is lost forever. Our hope here is for the enterprise to use this time window to provide some proactive mitigation techniques, like monitoring services for their clients' private information, or say devaluating old data like credit cards. So the takeaway of this talk is that Dragchute buys you this programmable time window that allows you to concretely differentiate between when a data breach has happened and when the data can actually be considered compromised. And it does so by not storing any secrets. And we also provide some proof of compliances that tell the legal authorities that we have our data, but we're taking the precautionary steps to protect it just in case a data breach happens. With that, I'd like to thank you all for listening, and I'd like to open up for the floor for any questions.
And we work in the same desk clump, so this could be a little awkward.
Oh,
but I was curious. I really like, my favorite part is the time locking part and the parameterization there. So I was wondering if What would you think about using like a memory hard hash function or something like that? So something that you can kind of control the rate at which you can compute it, and the way you can try to get around the time lock stuff. I was just wondering, like, how about a hash function or something?
So I think that process might be parallelizable. Correct me if I'm wrong, but I think the process would be parallelizable because you could do it in many different systems. So we wouldn't be able to provide this concrete time window that we want.
Okay.
Yeah.